Ladies and gentlemen, RIT graduates, we are so pleased to welcome a special guest to our celebration today, Nobel Laureate Dr. William Daniel Phillips. Dr. Phillips has, as you might expect, a most impressive list of achievements, a record of innovation and leadership in scientific research that is indeed inspiring. A native of Wilkes-Barre, Pennsylvania, he has been passionate about science all of his life, deciding as a young child it would be his life's work. Bill received a Bachelor of Science degree in physics from Juniata College, following in the footsteps of his parents, who, along with his siblings, also attended Juniata. He earned a PhD from another IT institution with an M at the beginning we don't talk about much here. And after 2 years as a Weizmann postdoctoral fellow at MIT, oh, I said it, didn't I? He joined the staff of the National Institute of Standards and Technology, then the National Bureau of Standards, in 1978. Dr. Phillips is currently leader of the Laser Cooling and Trapping Group in the Quantum Measurement Division of NIST's Physical Measurements Laboratory and a distinguished university professor at the University of Maryland. The research group he leads at NIST has been responsible for developing some of the main techniques now used for laser cooling and cold atom experiments in laboratories around the world. Dr. Phillips' work has been recognized and honored widely. He's a fellow of the American Physical Society and the American Academy of Arts and Sciences, a fellow and honorary member of the Optical Society of America, and a member of the National Academy of Sciences and the Pontifical Academy of Sciences. He is the recipient of the Gold Medal of the U.S. Department of Commerce, the Michelson Medal of the Franklin Institute, the Shallow Prize of the American Physical Society, and the Service to America Medal, Career Achievement Award. And in 1997, just to top it off, he shared the Nobel Prize in Physics for developing of methods to cool and trap atoms with laser light. Now, after hearing that long list of credentials, I can understand why you might be concerned that you're about to sit through a stuffy science presentation, but that's only because you've never heard my friend Bill Phillips speak. Be ready for anything. Now let's give a warm RIT welcome to Dr. William Daniel Phillips.
Thank you. President Dessler, platform party, members of the faculty, honored guests, and most important, graduating students of the Rochester Institute of Technology. Could somebody turn the lights on so I can see those wonderful students? Thank you. You are why we are here, and I'm talking to you. This is a wonderful day, a joyous occasion, a time for celebration, a time for fond memories, a time to look forward. You are receiving degrees from one of this great country's great universities, and you deserve to be proud of your accomplishments, and I am happy and honored to congratulate you for what you have achieved. I know you are eager to get on with this happy ceremony, to rejoice with your fellow students, and to celebrate with family and friends. But first, you have to listen to me give this commencement address. And I know how you feel. I've been to a lot of commencement ceremonies and heard a lot of commencement addresses, and they have been almost uniformly forgettable. There was one exception. The renowned cellist Yo-Yo Ma once gave a commencement address in which he advised all of the graduates that, like every musician, they must find their voice. What a musician does is give their own unique interpretation to well-known compositions, and the students, as well as all of us, have to find our unique ways through the familiar life experiences. Really good advice. But what made it memorable was that Yo-Yo Ma played his cello. It was awesome. So when Bill Dessler asked me to address you today, I was wondering, could I pull off the same trick? Could I, as an experimental physicist, do experiments in the same spirit as Yo-Yo Ma played his cello? We shall see. You ready to have some fun? As a physicist, what I do is I make things really, really cold. Why? Because when things are hot, it means the atoms and molecules that make up the stuff are moving around really fast. The molecules in the air in this room are moving at the speed of sound, about 300 meters per second. It's really hard to measure things that are moving that fast. And so what we want to do is we want to take a gas and cool it down so that the atoms in that gas are moving more slowly so we can study them and measure them better. So courtesy of this great university, I've got some really cold stuff. In here is liquid nitrogen. Nitrogen is the main constituent of the air. That means this is liquefied air. Unless you've been in a low-temperature physics laboratory, this is the coldest stuff you've ever seen. It is so cold that compared to it, the floor on which I am standing, in fact, everything in this great hall is burning hot. What would happen if you took cold water and poured it out onto a red-hot stove? It would boil. And that's what's going on here. This stuff is really, really cold. And if you've got something that cold, well, why not use it to cool down a gas? So that's the whole idea of what I'm going to show you now. So here I have a container of liquid nitrogen. Let me just put a little bit more in here to top it up. And here I have what I thought was going to be a very common container for hot gas, or as we say in the Washington area where I come from, hot air. But this is not at all a common container. This is a tiger balloon. Okay. So we've got the tiger balloon filled with hot air. Let's stuff it into this bait bucket filled with liquid nitrogen to cool down the air to make the atoms and molecules move more slowly. Oh yeah, this is so much fun. Absolutely. Okay, good. So now while that's cooling down, let's see what I can do to show you how cold this stuff really is. Here I have a Dewar flask. It's just a fancy name for a thermos bottle. It's been sitting out in the room all morning. It is, compared to the liquid nitrogen, burning hot. Imagine that you took a metal pail and heated it up in a fire until it was glowing red hot, and then took some cold water and poured it into the bucket. It would boil, and that's what's happening here. Don't try this at home. So while that's boiling away, cooling down the inside of the Dewar, let's cool down some more gas. Because after all, if you're going to do an experiment, you want to make sure you've got plenty of stuff to do it with, so we want to cool down some more hot gas. Okay. Wonderful, wonderful, wonderful. Okay, so now let's go over here. The boiling has subsided. Let me just top it up a little bit. So we got plenty of nitrogen in here. Now, here we have a nice fresh flower. Nice. It's been sitting out at room temperature. That means compared to the nitrogen, it's red hot. What would happen if you took a fireplace poker, heat it up in the fire until it's glowing red, and then plunge it into a bucket of cold water? It would make the water boil. And that's what's going on here. So I look in there and I see the nitrogen is boiling away, cooling down the flour. So while that's happening, let's cool down some more gas. Because, of course, the reason we're doing this is to make the atoms and molecules in the gas move more slowly so that we can measure them better. And we've got this incredibly cold stuff, so we're gonna cool down the gas to make the atoms and molecules move more slowly. You gotta stuff it in. You know, it's getting a little tight in there. Okay. Okay, good. Now, let's come back to the flour. The boiling has subsided. That means the flour is cooled down to the temperature of the liquid nitrogen. This flour is so cold that when I pull it out, it is frozen so hard, I can crush it like it was made out of glass. This stuff is really, really cold. And if you've got something that cold, well, you know, why not use it? What? Why not use it to cool down your gas to make the atoms and molecules move more slowly so that you can study them better? That's what the whole idea is. Yeah, there's still a little room in here. Okay, fantastic. Get down there. Okay. There we go. Now, let's see, what else can I do to show you how cold this stuff is? Here we go. A rubber band. Nice, stretchy rubber band. I'm going to take the rubber band and dunk it into this container of liquid nitrogen. Now, like anything that goes into the liquid nitrogen, it's making the nitrogen boil. It doesn't take too long. The boiling has stopped. The rubber band is down to the temperature of the liquid nitrogen. When I take it out, it is so stiff, I can break it like it was a dry twig. But all I have to do is warm it up in my hands, and it's a nice stretchy rubber band again. This stuff is really, really cold. And if you've got something that cold, well, and fortunately, we got plenty of tiger balloons. Then why not use it to cool down your gas so that the atoms and molecules will move more slowly so that you can measure them better? Okay. Let's see what else we got. Racquetball. Nice, bouncy racquetball. Let's see what happens when we put the racquetball in the liquid nitrogen. Now, how cold is this stuff? You know, when we measure the temperature of things, like the air outside, we usually use a scale like the Fahrenheit scale or the Celsius scale. On a cold day, it might go down to 0 Celsius. On a really cold day, it might go down to below 0 Fahrenheit. Physicists don't like these negative temperatures, and so we use a different temperature scale where 0 is the coldest possible temperature you could ever have. So this is called the absolute or Kelvin scale. On that scale, room temperature is about 300 degrees. Ice melts at 273 degrees. Dry ice has a temperature of 195 degrees on that scale. And the coldest air temperature ever measured any place on the face of the Earth, someplace in Antarctica in the winter, was 185 degrees above absolute 0. This stuff, which is so cold that it boils when you pour it out on the ground, this stuff is 77 degrees above absolute 0. Incredibly cold. For most of you, the coldest stuff you've ever seen. And so it seems perfectly reasonable, if you want to cool down a gas to make the atoms and molecules move more slowly, why not use it
the coldest stuff you've ever seen. But some of you, I perceive, have noticed there was something fishy going on here, that the volume of the balloons that went into this bucket was greater than the volume of the bucket. And the reason is that these balloons are as flat as pancakes. These things are Frisbees. These things are, whoa. Now, how many balloons did I put in? 5. And how many balloons did I take out? 5. And they were all tiger balloons, right? How many yellow balloons did I put in? How many blue balloons did I put in? How many red balloons did I put in? I could have put in balloons into this bucket until the cows came home, because what happened was that the air didn't go out of these balloons. As you can see, they've reinflated. What happened was the air condensed. It turned into a liquid or a solid or stuck to the inside of the balloon, and we didn't have a gas anymore, and that just won't do. Because we want to study our atoms in a pristine way, not stuck onto other atoms, not stuck onto a container. And so we had to develop another way of doing it. And I wish I had the time to tell you that story, because it's an incredible story. How we used light to shine on the atoms and push on them in such a way as to make them slow down. And not only did it worked better than anybody thought it would. And we eventually got the temperature of a gas down below 1/1,000,000th of a degree above absolute zero. That is 100 million times colder than the temperature of liquid nitrogen, which is, oh dear, it's out. Fortunately, I've got more. which is the coldest stuff that most of you have ever seen. It boils when you pour it out on the ground. Oh, I almost forgot. The racquetball. The racquetball. You remember how nice and bouncy the racquetball was? Broke like it was made out of China. Incredibly cold stuff, but we got gases 100 million times colder than that. And using that idea, we have been able to make clocks that only would gain or lose a few seconds in the age of the universe. So this turned out to be good for something. But now I want you to ask yourself, yeah, you thought it was just fun. And it is, but it was good for something too. But let me ask you this. You may be asking yourself this. Where do you keep the coldest stuff in the universe? You can't keep it in a cold bottle, because you've seen what happens if you try to put a gas in a cold bottle. It just condenses. You can't keep it in a hot bottle, because the bottle would heat it up. So you've got to keep it in a bottle that is something that has no material in it to hold your atoms. We use a magnetic bottle. Do you remember when you were kids and you played with magnets? And do you remember the first time you held 2 magnets in your hand and felt that they were pushing each other apart without touching? Isn't that amazing? I'm still amazed by that. We're going to use that, the fact that we can push on things without touching them, to hold our atoms, because it turns out that our atoms are little tiny magnets. And here I've got a big magnet, and here I've got a little magnet representing my atom, and I can feel that the big magnet is pushing up on the little magnet, and if I let go of it, it should float right here. And when I let go of it, it doesn't float, because it flips over and gets attracted to the big magnet. And if you ever tried this when you were a kid and you had a bunch of magnets, that's what always happens. It never works. But you learned something else when you were playing with toys as a kid. You learned that if you spin a top, it won't fall over. And it turns out that our atoms are spinning magnets, and so I've spun this thing, and now I'm going to lift it to the place where the magnetic field will hold it up. And it's not quite working. And the reason it's not working is your fault. And the reason it's your fault is because each one of you is putting out about 100 watts of heat, and that's enough to warm this magnet up just a little bit, and that makes it just a little bit weaker. So in order to compensate for that, I've taken a little bit of weight off, and we're going to try it again. And see if this works. Thank you.
That was fun. And it turns out that it's useful too, but why did I do it? I mean, what point did all of those wonderful fun tricks have in this commencement ceremony, where I'm supposed to send you off to the rest of your lives with some message, some profound words of wisdom? In that long ago graduation ceremony where Yo-Yo Ma played the cello, his message was, find your voice. A great message. But what is my message? It's simply this: I'm having fun, and I hope you will too. Now, maybe you were expecting something more profound, something along the lines of how your status as RIT graduates gives you a special responsibility, as Bill Dessler said, to make a positive difference in your communities near and far and in the lives of those you touch. And of course, that is true. But I think that you are both smart enough and good enough to have figured that out already. What you might have forgotten is that you can do all that while having fun. Doing science, as I do, is a lot of fun. In fact, doing anything that you love to do is a lot of fun. And one of the most important things you have learned in your time at RIT is how to have fun by exercising your mind. You've learned how to learn. I hope that you are going to use what you learned here at RIT to make the world a little better, and to do that, you will need to keep on learning. One of my favorite sayings is that a good day is a day when I learn something new and interesting. And as RIT graduates, you can make nearly every day a good day. You have that wonderful, inexpressibly exciting opportunity to take part in the life of the mind. No matter what you studied in your years here, no matter whether your career takes you in the path of those studies or not, you have opened the door to learning, and that door can never be closed. So my message to you today is, have fun. Have fun with your mind. Read, learn, do. You have what it takes. Your education may not be the ticket to a financially successful career connected to your field of study. That will depend on chance and circumstance, as well as on your own desires and your hard work and your ability. But your education is surely the ticket to a life of fun in learning and of using that learning to make a difference. Today is a day for celebration. I'm sure that today you will happily follow my advice to have fun, and you should. But what about tomorrow and the rest of your lives? The days to come may be filled with uncertainty. For what it's worth, that uncertainty is part of the human condition, and you're in good company. It's also a position of tremendous adventure. But as graduates of RIT, you are in even better company. You are in the company of those who have learned how to learn, who have access to the great adventures of the mind. You will celebrate and have fun today, but the real fun will be in what you continue to learn for the rest of your lives. Good luck.
Dr. Phillips is currently leader of the Laser Cooling and Trapping Group in the Quantum Measurement Division of NIST's Physical Measurements Laboratory and a distinguished university professor at the University of Maryland. The research group he leads at NIST has been responsible for developing some of the main techniques now used for laser cooling and cold atom experiments in laboratories around the world. Dr. Phillips' work has been recognized and honored widely. He's a fellow of the American Physical Society and the American Academy of Arts and Sciences. Ladies and gentlemen, RIT graduates, we are so pleased to welcome a special guest to our celebration today, Nobel Laureate Dr. William Daniel Phillips. Dr. Phillips has, as you might expect, a most impressive list of achievements, a record of innovation and leadership in scientific research that is indeed inspiring. A native of Wilkes-Barre, Pennsylvania, he has been passionate about science all of his life. You might be concerned that you're about to sit through a stuffy science presentation, but that's only because you've never heard my friend Bill Phillips speak. Be ready for anything. Now let's give a warm RIT welcome to Dr. William Daniel Phillips.
Thank you. President Dessler, Platform Party, members of the faculty, honored guests.
A fellow and honorary member of the Optical Society of America and a member of the National Academy of Sciences and the Pontifical Academy of Sciences. He is the recipient of the Gold Medal of the U.S. Department of Commerce, the Michelson Medal of the Franklin Institute, the Shallow Prize of the American Physical Society, and the Service to America Medal Career Achievement Award. And in 1997, just to top it off, he shared the Nobel Prize in Physics for developing of methods to cool and trap atoms with laser light. Now, after hearing that long list of credentials, I can understand why, deciding as a young child it would be his life's work. Bill received a Bachelor of Science degree in physics from Juniata College, following in the footsteps of his parents, who, along with his siblings, also attended Juniata. He earned a PhD from another IT institution with an M at the beginning we don't talk about much here. And after 2 years as a Weizmann postdoctoral fellow at MIT, oh, I said it, didn't I? He joined the staff of the National Institute of Standards and Technology, then the National Bureau of Standards, in 1970.